Hello there, my good YouTubers. Today I wanted to make a bit of an extra video because I'm sort of building a telephone recording circuit to capture data and audio that's going over my phone line for just general purpose recording, really. I have to say though, obviously in this video, that you know, the information's provided as is, and whatever you do with it, or whether you use it for any sort of ill use or anything like that, I'm not responsible for any of the actions. You're responsible for your own actions. That being said, I'm going to talk to you in this video, which I'll discuss how to break out data, as I've previously said, on audio signals travelling across a two-core telephone line. Most telephone lines today are all two-core copper wire. They don't use four-core really anymore. I mean, it still exists in certain places, but you know, it's pretty much always two-core telephone lines. And I'm going to make a circuit and show you how the circuit works, so that you can see it. Now this circuit will pretty much, you can do this and you can attach it to parallel in any sort of line configuration to capture any audio or, you know, data signals that's travelling over that line with the circuit, and you can do that undetected. I'll show how the circuit diagram works. I'll explain how the components, what they're there for, what they used, and what kind of output, certain things that you can change with the circuit yourself, you know, you can you know, to modify certain aspects of the circuit. Really, it's a very basic circuit. It's a very simple circuit, and as I say, I mean, this it's one of those things that can go through on data output through any of your audio input of your computer. And if you want to know more about how to use an audio interface as a data I/O, you can look at certain things. A good starting point is look at PSK, which used by amateur radio operators in sending messages across the audio signals through the radio on your amateur rig. So another thing to look at. As I say, that's you know, a good point of resource on that. Anyway, the circuit starts off like this, and the starting parts of the circuit, we obviously have two lines which come in, which is coming from your telephone line. We then we put a capacitor. Now these capacitors are not electrolytic capacitors. They're not the type that are polarity conscious, so they don't have a positive and negative. And what we're going to do is, in the circuit that I've done, I've used a 100 nanofarad capacitor here, and then what I've also done is I've added this in parallel. So I've got another capacitor here in parallel with the 100 nanofarad capacitor, which is also another 100 nanofarad capacitor. Now these are higher voltage. I've used on these ones here, which is actually here in front of me. Actually, I can actually show you the real thing. These here are rated at 1250 volts. So they're very high voltage. You don't want to use anything with the telephone circuit. You do not want to be using anything less than 250 volts on its voltage, you know, lines. We're using a Zener diodes, which are regulated at different voltage, but I'll explain those in a second. The next area of this circuit we have here is we have two resistors, and these resistors are set in parallel. I'll explain why I've put these in parallel, because, and the reason that these are in parallel is because you can only get if you want 5 ohms, let's say in a circuit, the best closest alternative to that would be a 4.7 ohm resistor. In my case, I want 5 kilo ohms or 5,000 ohms. So my alternative to that would be obviously a 4.7 kilo ohm resistor. Well, I didn't want 4.7 ohms. I actually wanted to go a little bit more accurate with the ohmage. So what I decided to do was use two 10 kilo ohm resistors and stick them in parallel. And by doing this, obviously with Ohm's law, which is V over IR, which we do in the triangle, which is a good way of remembering, it's voltage divided by the current to equal the resistance, or the voltage divided by the resistance to equal the current, or it's the current times the resistance to equal your voltage. In my case, what I wanted to do was, if I have 5 volts, which generally this line is, or most telephone lines are operating on 5 volts, I want to create a current flow around the circuit of 1 amps. So that would mean I need 5, if I have a 5 kilo ohm total resistance. So therefore I use two 10 kilo ohm resistors, which are available, and they are divided by each other when they're placed in parallel. If they're placed in series, they add on to each other. Rather than with capacitors, it's the opposite way around. When capacitors are placed in parallel, they add to each other. When a capacitor is placed in series of a circuit, like so, just in case anybody doesn't know what a series circuit is, they actually divide. Rather than with resistors, they're exactly the opposite way around. So let's get that clear. So this is why we have two 10 kilo ohm resistors in parallel to equal a good 5 kilo ohms, which in turn will leave us in Ohm's law. If we take the voltage and the resistance, the voltage divided by the resistance, which is 5 divided by the 5,000 or whatever, we end up with the current rating or flow around the circuit, which keeps my figures nice and balanced, and it keeps them accurate. This is also a very good way of trying to keep yourself undetected on the circuit, because if you have slightly fluctuations in certain current or whatever, then that affects parts of the circuit, and as I say, things like that can be detected. So this is the best way, if you can try and work things out as accurate as possible. It's the best way of keeping your circuit as undetected and unknown to the system as possible that you're connecting it to. And this was the principle in mind with these values. Then what we do is we come down here. Now what we use, and this is a very important factor on this point here, is in here I have a isolation transformer. Now you want to use an isolation transformer. You do not want to basically just make this circuit and stick it straight out. I mean, you will get audio out of it if you put it into any recording device. It's liable to, cause it to damage the device or anything like that, which can cause problems. So we have to put in to the circuit an isolation transformer. Now an isolation transformer is basically a one-on-one transformer, and everything on the telephone line circuits are generally a 600 ohm impedance isolation coils. In the United Kingdom we have a British standard. Everything that's used on every form of component that you need to use, especially an isolation transformer, which is one of these, has to be certified and has to come with a certificate to warrant the use of that component on telephone circuitry. This is exactly one of those components. It has a certificate, it's certified by the BS regulations for use on the British telecommunications circuitry. It's a very good idea to use these. This only cost me £5, so it's not a drastically expensive component, but it's a very good idea to make sure that you have got that certification, you have got that certificate. If there is any questions asked on putting a uncertified circuit on your telephone line or anything like that, or if there's any arguments from the authorities or anything like this, you can turn around and say, well, actually I've got the certificate, and you've used certified components. So this is one way of covering your ass on one avenue, and so on and so forth. So yes, I bought this from Radio Spares, or well, not Radio Spares, but RS Components here in the UK, which is a very common electronic supplier, should we say. And so yeah, they're readily available basically. There's a few of these. This is, as I say, this is 600 ohm 1-on-1 isolation transformer. So yes, and that's just a note on there. So we draw that in the circuit diagram like this, which looks like an inductor, but then we have, obviously on this side, we have the following inductor to represent it as a transformer. Little explanation on what the capacitors are for. Inside a telephone circuit, the current that's fed in here is DC. We do not want DC running round a transformer. It won't work. Transformers work on alternating current. They don't work on DC current. So what we want to do is isolate the DC current, or sorry, the DC voltage from the circuit. We do this by adding the capacitor in. The capacitors filter out the DC flow around the circuit. What is with the values here? Well, the reason I use two capacitors is because if you try to get a 200 nanofarad single capacitor in a voltage greater than 250 volts, it's incredibly expensive. It's a lot cheaper just to use two 100 nanofarad capacitors to equal the 200 nanofarads, because they're obviously adding themselves together as they're added in parallel. You can break this up and you could put 4 in there, and I worked this out. There is available 4 47 nanofarad capacitors, so you could put 4 capacitors here in parallel, as so, which in turn at 47 nanofarad will be 47 nanofarads times 4, which isn't 200 nanofarads, but it's pretty close. And being as what we're doing here is the primary purpose is to isolate DC, and I'll tell you why the values of the nanofarads are there in a second, but to isolate DC is the first aspect of it, so only allow AC signals to pass through, because this will filter and block DC current, and only allow an AC signal when it comes through, which is going to be your audio signal or data signal, however, whatever it is that you're capturing. So that it will only allow an AC signal to pass through the capacitors into the isolation transformer, and out of the isolation transformer comes the signal that you're going to be using. So in this case, how do we work out what is this with the values of capacitor? Well, the values of these capacitors are here, and they're worked out, and I worked them out to about approximately 200 nanofarads, is because we want to filter out interferences. In telephone circuits and things like this, they use it picks up or induces interference currents approximately 50-60 hertz, sometimes higher frequencies, this, that and the other, which are picked up from the standard mains lines, or even a mains transformer that is being used on the line to power in the little green boxes, you know, to power the line so that you've got the voltage coming over to power your phone. They are not super clean. So what we want to do is, I've chosen 150 hertz, and what I want to do is make sure that anything below 150 hertz is not allowed to pass through the circuit. So what effectively we have here is a high pass filter. And if you wish to learn a lot more about high pass and low pass filters and how they work, they're very simple. It's just getting your head around them, and I don't expect this video necessarily to give you the entire explanation of low pass and high pass filters, but if you want to look into that, and you can use a few SPICE programs, computer programs, which will certainly teach you a good, you know, a good sort of lesson in how you can calculate and work out high pass and low pass filters. There is a formula involved in this to calculate this out. I don't think the formula, I tell you what we'll do is I may give you the formula to just so you know what the formula is in this video. And this is, I just have to get my, I can never always remember the formulas off by heart, but you can calculate your formulas out here, which is simply done by 1 divided by 2 pi, yes, that's pi as in pi meaning 3.14, or if you've got that on a scientific calculator, you can do that on your calculator. Which is then multiplied by the resistance, which in turn is multiplied by the frequency. Or if you wanted to work out that would work out your capacitance. If you wanted to work out the frequency, you would rearrange the formula and C would take the place of F, so you would be 1 divided by 2 pi omega C. This is your formula, and this would calculate your frequencies. And if you put in 200 nanofarads, which is times 10 to the power of 6 decimal places, which would be 6 zeros, that would be 0.00000 to the 6 decimal places of a farad, which you would put in here to your 5,000 ohms, and you would find that this comes out at approximately 159 hertz, which is anything less than that I want to block off. So this circuit will not allow any frequencies lower than approximately 150 hertz, which is what this is all about. You can make modifications if you want to allow that. I don't know why you would, but as I say, that's all that's here. Now what we do is we have another section of the circuit which I will add in here, and this is a protection part to the circuit. Protection in the circuit is very important for your own equipment, not alone other people's equipment. So for argument's sake, we are going to put a Zener in this circuit. Now these Zeners here are regulated for 2.7 volts each, and they're called what we refer to as a back-to-back system. You can research more about Zener diodes on the internet for more information about how they regulate voltage, which is again basic principles of Ohm's law, which is they vary the current to match the voltage. As I say, you know, that's a little out the scope of this video, but for the purposes of this video, the basicness of the back-to-back circuit is used for clipping, and the process of clipping is, I'll just show you, I've got some printed out some documentation to assist in this. The process of clipping, which is exactly what we have here, which is the back-to-back side circuit, is so, obviously these values are different, but it's so that we can take the peaks of the AC current. Obviously this taking the peak of the reverse bias, this taking the peak of the opposite side of the AC circuit. So we can clip the amount or the maximum amount of voltage as the amplitude of a signal here is its voltage. So we can clip these areas here and regulate to a reasonable level what we want to pass through the circuit. And in this case, obviously, what we start with is 5 volts. So we have amplitude voltage here, which we then can regulate at 2.7, which adjusts via the current differential to the voltage. So that's a small explanation on that. That's just a clipping device which is a safety device to sort of not allow too higher peaks of amplitude to pass through the circuit. For instance, in a sense like a compressor, to not allow when somebody shouts down the phone, for instance, it won't humongously peak here to the point that you'll end up with your microphone circuit or input line circuit or anything like that to become overloaded with a massive amplitude. And this is just a basic protection circuit to clip the AC signal that you're wanting to extract or break out from the line. A good line of protection to place into your circuit. Furthermore, on the end here, and this could be done further modifications, I place a little piece of rubbish under there. I place a 820 ohm resistor. I shouldn't have put that there, but let's just stick that like that. This resistor here is just to resist the intensity of this. It's sort of like a volume control, if you want to put it that way. If you find that the volume is too low, you could lower this resistance slightly and in turn increase the volume. If it's too loud or whatever, you could increase it. You could even, if you wanted to, put a potentiometer here. You could even do a potential divider, which would basically you would take a variable resistor like so, and you'd have your resistor here to here, up to here, and obviously as you varied the potentiometer, it would in effect vary the volume. I mean, you could do that out of modification to the circuit. That is it. There is nothing more to this circuit. It is as simple and as clear cut as that. There is nothing else more to it. And there's nothing else really more to understand. However you wish to design it, you can put it on the Vero board, which is like what I'm doing, to save etching. And this is this strip board here, which, as you can see, has all the straight lines with the holes placed in them. You can do that, which is the very old-fashioned style of method, so that's not a problem. Put it into a box, anything you want to do, quite easy and efficiently. And that's it. That's all you need to do. On this end you can stick crocodile clips, or you can put a telephone socket on it, very much like what I'm going to do, with a telephone socket on here and then take it out on a 1/4 inch 6mm, if you want to call it that, jack. So that's what I'm going to be pulling it out here on, and that's it. There is nothing else to the circuit. So it's as simple as that. If you wish to, build one of these and use one of these are a great circuit. They're good balance, and they obviously got the protection system in there, so it doesn't blow up, either your mixing desk, or it doesn't blow up your recording device. And because of the way that the circuit's done and get well balanced out, it means that you can remain undetected as much as possible, because you're not interrupting the telephone line in any way. So there you have it. It's that's the whole circuit. So yeah, there you go, my good YouTubers. Hope that gives you some ideas into breaking out the signal across your telephone lines. Anyway, speak to you again, my good YouTubers. Take it easy. Stay safe. Bye-bye.